Welcome to the lecture series number 7 for spectroscopy. We are discussing ultraviolet spectroscopy. In the previous series, we were discussing about the property of light, electromagnetic radiation, ultraviolet region, Beer-Lambert's law, and the principles of the ultraviolet spectroscopy, particularly the excitation levels. And the previous session, that is session number 6, we started with an instrumentation part. In the instrumentation part 1, we discussed the source of light and what are the lamps are used and what are the conditions to select the light source. Now in this session, we will discuss the grating. I think you're able to visible the diagram. In a prism, white light enters into the prism, the dispersion takes place, and it deflects into, and it splits into several colors. The same way, the diffraction grating is there. When a white light falls on the diffraction grating, the same like dispersion, here also the colors get dispersed. And with the help of a slit, we can select the light source which we required, or in which wavelength we required, we can select it. So the grating is a dispersive element used to select the wavelength required to probe the electronic transition of a samples, chromophores. We are discussing about chromophores. The chromophores are the things which have a conjugation, and the presence of the electrons in those regions will give excitations, and it gives the color deep depth to the compound. It is rotated, that is grating, the rotated to the wavelengths, and the wavelength gets selected. So whatever the wavelength we require, that we can select, and diffracts the light into a several groups. So the direction that the light is diffracted, in which direction it gets diffracted, it depends upon the angle and the wavelength of the incident beam, and the grating's groove frequency, or a number of grooves on the grating per millimeter. So while selecting a monochromatic light, so we have to set a specific wavelength. The light emerging is not perfectly a monochromatic one, but contains a range of wavelengths. The total energy at the exit slit of the monochromata at a specific wavelength has an intensity distribution of an isosceles triangle like this. You see this triangle here? Yes. The peak of this triangle is the target wavelength, and the spectral bandwidth is the full width half max. We call it as FWHM of the triangle. The bandwidth should be set to 1/10 of the sample peak's FWHM. The differentiate peak in the spectrum, the bandwidth, and the silt width needs to be adjusted. To get those, the width of the silts to be adjusted. The instrument's ability to separate light into a defined wavelength region is known as a spectral resolution. To get the spectral resolution, we have to adjust with the silt and the desired angle. The narrower the bandwidth, and therefore the slits, the better the resolution. However, since less light will pass through a narrow slit, the spectrum will have a more noise. So likewise, a wider slit and the bandwidth increases, the light throughput, and therefore the signals would produce a poorer peak. Look, these 2 points: less light, narrow slit, more noise. Wider slit, increase in bandwidth, poor peak resolution. The goal is to find a balance between these two, a good resolution with very low noise. So please look into this picture. There are two waves, one represented in blue color and another one is a pink color one. The pink color one is 1 nanometer bandwidth and this one is a 5 nanometer. As the bandwidth increases, the peak collapses and it becomes broader. So the bandwidth increases, that is 5 nanometers. The peak is get collapsing in some areas and it becomes broadening. But in 1 nanometer bandwidth, we'll get a narrow one. So in the instrumental part, now we are discussing about monochromata, in which how the grading should be placed and how the bandwidths to be fixed to get a narrow or broadened waves. Thank you. We continue this instrumentation in the next session. Thank you.